Hello, everyone. Welcome back. I hope your first week of classes have been going smoothly. Today, we're going to start a new unit on counting, and we're going to cut this up into two separate pieces. So we'll do our part one today, really doing some basic rudimentary things. And then in part two, a little bit more complex and more complicated problems that we'll work on that will eventually help us when we do our probabilities unit next week. All right, so in our first example, we're going to suppose that our wardrobe consists of the following. We have 2 pairs of jeans, 3 shirts, and 2 pairs of shoes. So instead of writing out all this information when we do this problem, I'm just going to say J1, J2 are the 2 different jeans I have. S1, S2, S3 are the 3 shirts, and then H1, H2 are the 2 pairs of shoes that we have here. And what we want to do is decide how many distinct outfits we can make using one of each item. So I want 1 pair of jeans, 1 shirt, and 1 pair of shoes to make out my outfit here. So this is really the overall idea that we want to do here. With all of these options and different categories, how many choices do I have depending on the situation that we're working with here? Okay, so let's start with the jeans. I really have 2 options with my jeans. Again, I can choose J1 or J2. Okay, and then for each jean that I choose, I have a different shirt that can go along with it. So I could have picked the first, the second, or the third shirt. And I could have done the same thing with my second pair of jeans, the first, the second, or the third pair, or the third shirt. And now within these choices, after I've chosen a jean and a shirt, I now have the choice on what shoes I want to wear. So if I choose jean 1 and shirt 1, I have the options of wearing either the first pair of shoes or the second. And the same is true for every other choice that I made. So here, if I follow any one of these branches, so let's say jean 1, shirt 3, and shoe 1, pairs of shoe 1, then this really is telling me one choice that I have. And so if I count all of the different choices I have here, this is the total number of distinct outfits I could make, right? There's no repetitions here, and there's no other options that I could have made. And if I count these up, I'll get 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 options. So 12 different outfits that I could make. Okay, and here you might notice that I could write 12 as 2 times 3 times 2, the number of jeans times the number of shirts times the number of shoes. And this is not a coincidence. So we'll see in our next theorem that this is exactly how we want to do this counting. Instead of writing out all of the different options that we have, we want to do this much faster. Decide how many options do I have for the jeans, how many for the shirts, how many for the shoes, and none of them depend on each other, so I can really just multiply them together. So here, our fundamental principle of counting, and lots of times I might just shorten this as FPC, is going to tell us the total number of possible outcomes in a series of decisions that you're making. This can be found by multiplying the number of decisions or categories in the following way. So first, we can draw a box for each decision or category. Here, there's 3 decisions I need to make. I need to choose a bottom, a top, and a pair of shoes, so jeans, shirts, and shoes. So there's 3 decisions or 3 categories that I have. And then within each box, I'm going to enter the number of choices for that decision. So again, let's remember the first choice I have is jeans, then shirt, then shoes. And within my jeans, I have 2 options. Within my shirt, I have 3. Within my shoes, I have 2. And then the last step is just to multiply all these together. And this does give us back 12 in a much faster way instead. Right. And notice I could have chosen the shirt first, then the jeans, then the shoes, that would have changed this to 3 times 2 times 2, but this ultimately will give me the same answer back. Okay, so let's look at our next example. And again, instead of writing out all of the possible options and then counting them, let's use our fundamental principle accounting by writing out all these boxes with all the different choices we need to make, and then deciding within each one of those boxes, within each one of those categories, how many choices do we make within that. Okay, so we're going to make a password consisting of 2 capital letters, followed by 5 digits. And let's remember, when we say digits, we mean the numbers 0, 1, 2, 3, all the way up to 9. So 10 is not included, but 0 is. These are all our digits. Okay, and we want to decide how many passwords can be made in this way. So the first thing that we want to realize is that we have 2 plus 5 different choices that we need to make, because there's really 7 positions in our password. So I should really have 7 boxes. Let's see, did I do that right? 3, 4, 5, 6, 7. All right. And in my first 2 boxes, they're going to be capital letters that I'm allowed to use. And in my last 5 boxes, the digits, these all can be digits here. So what I need to decide is, in the first box, if I'm allowed to use a capital letter, how many options do I have? And here we'll be using the English language, so we'll have 26 letters we can choose from. Okay, in my second box, this does not depend on the choices I made previously, so I can use any one of these 26 letters again. And now within my digits, I have 10 options, the numbers 0 through 9. And again, for every single one of these, I have the same number of options. I can use the same digits over and over again. If I were to write this in shorthand, multiplying this here, I could write this as 26 squared times 10 to the 5th power. This is our shorthand for multiplying the same number over and over again. If I put this into the calculator in this way, it would look like 26, and then I'd find the caret symbol that's on top of above the division symbol. Then I'll press 2, then times my 10 to the power of 5. Or I can do 26 times 26 times 10 times 10 times 10 times 10 times 10, but this just lets me do this a little bit faster. Okay, and when I put this into my calculator, I should get back 67,600,000. So this is the number of ways that I can make a password that consists of 2 capital letters followed by 5 digits. Okay, so let's change the problem slightly. And let's decide that we're not allowed to use the same letters or the same digits. Nothing can be repeated within my password. Every single part of my password has to be distinct. Again, no repetition. Okay, this is going to be an important concept that'll help us kind of distinguish the different types of way of counting. Will depend if we want to repeat or not repeat. And then also we'll see if the order matters or does not matter. But we'll get to that later on. Okay, so we still have the same 7 choices to make. Again, I have non-repeating capital letters. And then I have non-repeating digits. And this is going to work slightly different. And so here, let me just start from the left. If this is the first choice that I'm making, I know I need to use a letter that has not been used, but because I have not made any choices already, all 26 letters are allowed. And now let me make my choice for my second box. Now here, again, I need a capital letter that's not repeating, but I've already picked a letter. So this is saying I'm allowed to use every letter except for the one that I used previously. So here I originally had 26 options, but because I already picked one letter, I now have 25 options for the second box here. Okay, so that's taking care of all the letters. I don't have to worry about repeating any more letters because I won't be using them. And so now I'll start with my digits. If this is the first digit that I'm choosing, all 10 options are allowed. Now it's my second digit that I'm choosing. I can no longer use the digit I used previously. So I have 10 minus 1 options, or 9. Okay, now for the third digit that I choose, I've already chosen 2 digits. So I have 10 minus 2, or 8 options here. And we can see the pattern. I don't want to repeat the first 3, so I have 7, and then I have 6. And I'll multiply these together. And there's no nice shorthand at the moment that we have to write this in your calculator. So you do have to write 26 times 25 times 10 times 9 times 8 times 7 times 6. So here I see, after putting this into my calculator, that I have 19,656, excuse me, 19,656,000 different passwords. So these are all the options I had for my passwords when I'm no longer allowed to repeat any digits or any of my letters. So I did shrink the number of possible passwords by adding this restriction about not being able to repeat. Okay, so often what we're going to want to do is we're going to want to count the number of ways to rearrange, or what we call permute, a set of objects. So let's say I had 4 objects that I wanted to rearrange, and I want to decide how many ways can I do this. So I have 4 spots for my 4 objects. So spot 1, spot 2, spot 3, spot 4. And I don't even care what the actual objects are. I just know that I have 4 different objects to choose from. So here, if I figure out my first spot, I have 4 objects possible. But I want to rearrange all these 4 objects at once. So really hidden behind here is that there's no repetition. This is saying the object that chose for spot 1 can no longer be chosen for spot 2. So less like last time, we'll be going down by 1 every single time because we have 1 less choice in my objects. So for spot 2, I have 3 options. For spot 3, I have 2 options, and I only have 1 object left. And so this is the only choice I have. And then I'll multiply these numbers together. Okay, and when I do this, I'll get back 24. Okay, this idea of multiplying numbers as they're descending until we get to 1 is going to be really important to us. And so we're going to give it a name. And this is going to be our factorial. And we'll see in a second how we'll do this in our calculator as a way to check our work. And again, this pattern does show up very often, which is why we give it this name here. Right, so when I have a number n, so I'm going to write this like the general form for the definition, and then we'll actually work with more numbers to practice and to see how we can manipulate these numbers more easily. So here, if I had a number n, what I want to do is I want, for n factorial, is I want to multiply n by every number smaller than it until we get to 1. And I only want to include whole numbers, so I'm just going to be subtracting by 1 every single time. So I want to go down, I want to subtract 1. That's the next number I'll multiply by, then subtract 1 more. That's the next number I'll multiply by, and I'll keep doing this until I get down to 2 times 1 all the way at the end. This is the place where I stop. And honestly, we could just stop at 2 because multiplying by 1 won't make a difference here. But this is our definition here. Okay, so let's see how to calculate some of these numbers by hand and just really practice what this notation means. And then we'll also talk about what this will look like in the calculator, how to find this in the calculator. Although I do expect you guys to be able to do this by hand, but we can use the calculator as a way to check our work. Okay, so here for my 6 factorial, 6 is my n. So what I want to do is I want to multiply 6 by 6 minus 1, which is 5, times 6 minus 2, which is 4, all the way down until I get 3 times 2 times 1. Really all the way down until I get to 1 here. Okay, and if I put this into my calculator, I'll get back 720. Okay, and in my calculator, if I want to do 6 factorial, the first thing I need to do is press my 6 number, and then I need to find my factorial button. This is going to be under the math button. Lots of things that we'll use is going to be under this math button. We're going to scroll to the left until we get to the column that reads PRB for probability. And then we're going to click the number 4, or you can scroll down to the 4th one, which is exactly where the factorial button is. Okay, and then to actually use it, or you'll see on your screen 6 factorial will show up now after you clicked on the factorial button. And so you can press enter to get your result, and you should get back 720 here. Okay, so what we're going to do is we're going to see when we do our probability section, we're going to have, and actually in our counting as well, we're going to have lots of these factorials being divided by each other, but we don't want to have to write every single term every single time. We're actually going to find some shortcuts to be able to do these calculations much faster by hand. So we'll do this first one the long way, and then we'll see how could I have done this a little bit faster. And luckily, these numbers are not too big, so the list of things that we're multiplying are not very long. But here at the top, we'll have 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. So we're multiplying all of these numbers from 8 all the way down to 1. And now the denominator downstairs, we have 5 factorial. So we're going to have 5 times 4 times 3 times 2 times 1. Right, and what we're going to notice is this smaller factorial that's showing up downstairs is also showing up in the bigger factorial upstairs. Right, I see that because I'm multiplying upstairs and downstairs, I'm going to be able to cancel very nicely. So I'll cancel the 5 with a 5, 4 with 4, 3, 3, 2, 2, 1, 1. And I'm only going to be left with 8 times 7 times 6. But I actually could have done this a little bit faster. So I don't have to list every single number. I can decide which is the smaller factorial. That's going to be 5 factorial. And I'm going to see that show up inside of my 8 factorial here. So I can write this as 8 times 7 times 6 times, now I have 5, 4, 3, 2, 1, or 5 factorial, which is exactly what's showing up downstairs. And because I'm multiplying, I can just cancel these out. So I have a much faster way to simplify my work instead of writing every single digit that shows up in my product. And then I can put this into my calculator to get 336. We'll see eventually, like in part D, I have something like 52 factorial. I do not want to write every single digit, 52 up to 50, or all the way down to, up to 1, right? This is why we want these techniques to kind of simplify our work much faster. Okay, so let's do the next one here. And this one looks a little bit different because I have multiple products showing up. But I noticed that up top and on the bottom, I have a 9 factorial and a 7 factorial. And I'll see in my 9 factorial, a 7 factorial will show up. So this is the one that I'm going to manipulate. I'll have 9 times 8 times 7 factorial. This is just taking care of the 9 factorial here. Times, and I'm just going to write out the 3 factorial, 3 times 2 times 1. Likely there weren't that many terms. And then downstairs, just that 7 factorial that I saw showing up upstairs. So I can easily simplify this, or at least easier than writing down every single number that shows up. And now this is the product I'll put into my calculator. And again, if I just wrote 9 times 8 times 3 times 2, this will give me the same answer because multiplying by 1 doesn't actually change your number. So here I would get 432 back out. Okay, this part D, this is one that we'll see more more commonly with our counting problems. This type of quotient, you'll see this pattern showing up later on. Okay, so upstairs, we have a 52 factorial, and downstairs we see a 50 factorial. So to be able to cancel as many terms as possible, I'm going to rewrite my numerator, 52 factorial, as 52 times 51 times 50 factorial. Right? I technically had the choice of writing upstairs to have the 2 factorial or the 50 factorial, but this makes it much easier for me because I cancel out a lot more terms this way. Then I'll leave my 50 factorial the same downstairs because I'm just going to cancel, and then I'll rewrite my 2 factorial as 2 times 1. Okay, now we'll do my cancellation, and I can write this as 52 times 51 over 2. I could try to simplify this fraction, or I can just plug it into my calculator like this, where I would do 52 times 51 divided by 2. And here, if I do this, I'll get back 1,326. Okay, let's look at the following one. Here, this one's simpler because I don't have really any options. I'm going to write 70 factorial to have that 66 factorial show up. So I'm going to stop when I see 66. So I'm going to do 70, 69, 68, 67, and then 66 factorial over 66 factorial. So I can cancel these pieces out, and I'll get 70 times 69 times 68 times 67, which will give me a very big number, 22,005,480. Okay, something you'll see, this is the reason why we want to be able to do these these shortcuts by hand, or these calculations by hand, is because if I tried to put this into my calculator, 70 factorial over 66 factorial, I would get an error. It turns out that the calculator cannot handle 70 factorial. It takes too much space in the calculator because 70 factorial is a very big number. Does not have enough space in it to be able to calculate this, to be able to show you what number we're working with. And so it just gives you an error, tells you it can't compute it. So this is why we want to feel comfortable doing all these calculations by hand. Right? It turns out that this is the first number that the calculator cannot compute. It can compute 69 factorial, but the way that it gives you the answer is not very obvious what the number is, and it's actually a very big number. Okay, if you put this into your calculator, it'll give you 1.711224524 times 10 to the 98th power. This is a fancy way of saying move your decimal place over to the right, 1, 2, 3, 4, 5, 6, 7, 8, 9, and keep going 98 times. This is going to be a massive number, which is why the calculator has to write it in this form to be able to tell you what it is. But as soon as I multiply this by 70, it's going to become way too large for the calculator to be able to calculate. And so that's why 70 factorial does not give you back an answer. But 69 factorial does. It just doesn't give it to you in a nice form here. And let me actually make sure. Sometimes they write it in a different format. Yep. So in the calculator, it'll actually say E here, E98. And that's the fancy way of saying multiply by 10 to the 98th power. So that's really what that means there. Okay, so this is the biggest factorial the calculator can compute. And even then, the way that it gives you the answer, it's almost unreadable. It's not really obvious what the number is here. Okay, so this lecture was pretty short, right? Just kind of doing some of these basic ideas that we're going to need for accounting, where we're going to talk about what happens if I'm I am allowed to repeat or not allowed to repeat one of my choices. What happens if the order matters? Oh, actually, I take that back. We are going to continue. We do have 2 more pages worth of material here that we're going to get through, but not too complicated. And really what we're going to think about is when is your order going to matter or not matter, because that's really going to be the 2 big distinctions that we'll have. Sorry about that. Okay, so our special case here, we want to be able to calculate 0 factorial, but it doesn't follow our definition nicely because I need to be multiplying by numbers as it descends all the way down to 1, but 0 is smaller than 1. But this number is going to show up, so we want to give it a definition. So anytime we see 0 factorial, we know that the answer is just 1. Okay, and we'll see this eventually, but we just want to make sure we know how to do this when it comes up. Okay, so our fundamental principle of counting, or FPC, allows us to determine the total number of possible outcomes when a series of decisions must be made. And so far, all of our examples involve selecting one item from each one of our categories. So I only wanted 1 pair of jeans. I didn't want 2 or 3. I only wanted one shirt. I didn't want 2 or 3 on that either. And I only wanted 1 pair of shoes here. But what we're going to see is that we'll have plenty of more situations where you need to choose more than one item within each category. And when more than one item can be selected, the selections can either be made by replacing or not replacing that item. And it's going to depend on our context here. So let's look at our example here, where we want to select a 4-digit PIN. Remembering digit means 0 through 9. Okay. In this case, the digits can be selected more than once, so we are allowed to replace it. We can have repetition. And we want to count the total number of pins possible, right? So this is a problem that we could have done previously, where I have 4 choices to make, 1 for each digit in my pin. And I'm allowed to plug in a digit, and I'm allowed to repeat. So all 10 digits are allowed in every single one of my positions. So this is 10 to the 4th, 10 multiplied by itself 4 times, which I can write in this way in my calculator, or I can multiply 10 by itself 4 times instead. And this gives me back 10,000 pins. Okay. It turns out when we have this replacement, it's much easier to calculate. When we don't have replacement, when things are not allowed to repeat, especially if you're working with people, the situation is going to be a little bit more complicated. And this is really what we're going to talk about for the rest of this lecture and the lecture coming after. So again, we cannot select an item more than once. So say we wanted to make a committee of 3 people from a pool of 10. Once you select a person, they are no longer a candidate, right? A person can't be on the committee twice. So here we see we want 3 people in our committee out of a total of 10. Okay, so I have 3 choices to make, 1 for each committee member. Noticing that I cannot repeat without replacements, or you can think without repetition. Can I have 10 total people I can choose from? So in my first box, I have 10 options. In my second, I can no longer use that first person. So I have 9, and then I have 8, right? And I can multiply these together to give me a total of 720 ways here. Okay, and we're gonna see that somehow our factorials are gonna come into play. So this is not giving me back 10 factorial, but I can actually write this as 1 factorial divided by another. But even before we do that, let's just think about if I had 3 people I was trying to choose from a total of n, how can I do that? Right, remembering that I can't do this repetition now. Okay, so here, if our committee only needs 3 people, then the number of ways to form a committee from a pool of n people can be found using the following. For my first box, and here I'll draw my 3 boxes here. I have n choices. For my second box, I have n minus 1. And for my third, I have n minus 2. I can write this as n minus 1, n minus 2. And what we're going to see later is that we're going to have a nice formula in terms of our factorials that will do this much faster for us, just knowing how many choices are we making out of what total pool. Okay, but it turns out that lots of times the order is going to matter. And so we need to be able to decide when the order matters or does not matter. Okay, so let's say in this situation that our committee members are going to be paid, where the first person that I pick gets the highest pay, the second person that I pick gets the middle pay, and the third person that I pick gets the lowest pay. So what we want to be able to decide is, does the order matter? If I choose, let's say, Alice first versus second, is that going to matter to her? Will the order matter here? And it turns out that it does. So here, whether I choose you first or second is different because the pay is different. So really the positions, I can tell a difference between them. They are distinguishable. And so here I'm going to say order does matter, because if I choose you first, second, or third, will give you a different outcome. Okay, and when the order matters, what we're going to say is we're going to call this outcome a permutation. Okay, and when order does not matter, we're going to call this a combination. So when we were just picking committee members where it didn't matter, everybody got paid exactly the same. Order would not matter, it would be a combination. As soon as I make the pays different, the order will matter, and I'll make this a permutation instead, or I'll call it a permutation. Okay, so for the rest of the lecture, for the rest of the video, we're just going to look at some situations and decide, does the order matter? Does it not matter? And then decide, does that mean is it a permutation or a combination? Just to help us remember what these words mean here, and to help us decide what the context is. So let's say we are selecting individuals for a team. Okay, and really, you can't tell the difference between if I pick the first, second, or third, because they're all just going to be part of this big team where no other choices were made. So we're going to say here, order does not matter. Okay, and when order does not matter, this is a combination. Okay, let's change it slightly. Let's say we selected individuals for a team by position. So let's say if I was picking a team for a soccer team, and the first person I chose was the goalie, the second was a forward, and so on. So depending on when I chose you, it dictated which position you were going to be. So here we can see, depending on when I choose you, it will make a difference. The positions are different from each other. So in this example, order does matter. So we're going to call this a permutation, since each position is distinct. Okay, let's say we're selecting desserts from a menu. Here, it doesn't matter how I select them. So again, the order does not matter. So we call this a combination. And let's change it again. Let's say we select our 3 favorite desserts in order. So our favorite, second favorite, third favorite from a menu. And it really doesn't matter what the numbers are here. We're just deciding, does order matter, does it not matter? And here, because I'm giving it an order, order is going to matter here. Right? I'm really saying the first is my favorite, the second is my second favorite, and the third is my third favorite. So order does matter here. So this is a permutation because each position is distinct. Okay, let's look at the last two. We're going to select a sequence of numbers for a lock. So we need to decide if I pick 1, 2, 3, will that be different than 2, 1, 3? Right? Will the order actually matter here? Because I'm working with a lock, it is very specific in which order I have to make the choices. So the order does matter here. So order does matter. So this is a permutation. This one's more of a context. You need to understand the context of a lock. Right here, the position is distinct, even if they don't outrightly say it in some form. Okay, and the last one, let's say we select numbers from a lottery ticket. So here, and maybe you aren't very familiar with lottery tickets, but all that matters is that your number shows up on your ticket. They don't care what order it's selected. It's just dependent if the number is on your ticket there. So the order does not matter, and this is going to give us a combination. Okay, these are decisions that we're going to have to decide in our problems in part 2. So really just to get us comfortable deciding, does order matter, does order not matter, and what that means in terms of a permutation or a combination, because we'll have specific formulas for each one's there. But next time we'll do all this and we'll actually count the number of ways that we can make these choices here. All right, have a good one.